AP Review Session, Lesson 5. In this lesson we'll take a look at gases. We'll take a look in Lesson 5 at some multiple choice questions from the AP exam, and then in the next session we'll take a look at some free response questions. So let's begin with more of a qualitative type of question. Here we say that a rigid metal tank contains oxygen gas. Which of the following applies to the gas in the tank when additional oxygen is added at constant temperature? So we have ourselves a tank, closed tank with oxygen gas in there, and then we're going to add more oxygen gas to it, is the idea. A says the volume of the gas increases. This is incorrect because the tank is rigid, so volume stays the same. So this one's out. B says the pressure of the gas decreases. This is actually the opposite of the truth. Because we're adding more gas, the pressure goes up. So this is also out. C says the average speed of the gas molecules remains the same. Now this is true because the speed of the molecules is related to the temperature. And since the temperature is constant, it does not change, the speed of the gas molecules does not change. So C is the correct answer. The reason why D is not the correct answer, it says the total number of gas molecules remains the same. This is incorrect because, again, we're adding more oxygen, therefore increasing how much gas we have. And E, the average distance between the gas molecules increases. This is not true. Usually, when volume stays the same, the distance between molecules stays the same. It's when volume changes that the distance changes. So that should do it for example 1. Example 2, another question. Actually, this one is more quantitative. So we have a 2-liter sample of N2 gas and a 1-liter sample of argon gas, each originally at 1 atmosphere and 0 degrees Celsius, are combined in a 1-liter tank. If the temperature is held constant, what is the total pressure of the gases in the tank? So we have a tank with N2, and this is 2 liters. Then we have a tank of argon, 1 liter, and both of them are at 1 atmosphere. This one's 1 atm and this one's 1 atm. Now we're going to put them together and then combine them in a new 1 liter tank. And they want to know what is the pressure. That's kind of the idea. Now this is actually pretty simple, but the answer is going to be simple. However, to get there, there's going to be a little bit of a misconception that we'll have to clear up. It turns out that if we were to think about combining these two gases into a 3-liter tank, and we have 3 liters, it turns out that the pressure will still be 1 atmosphere. And the reason the pressure is still going to be 1 atmosphere is because these were in separate tanks to begin with. So if we just you think about just combining these together, the pressure doesn't really change when we combine the two. So the pressure is still 1 atmosphere for the whole tank. Well, you can say we increase the volume to 3, but then the pressure is compensated for. So what we do then is we're going from 3 liters down to 1 liter. And you can use, we showed you the ratio method. You can use this method where we have volume 1 and volume 2, and then pressure 1 and pressure 2. So our volume 1 is 3 liters, our volume 2 is 1 liter, our pressure 1 is 1 atmosphere, and we're trying to find out what the new pressure is. So based on Boyle's law, volume and pressure are inversely related. As volume goes down, pressure goes up, and vice versa. So here we see the volume go down by 3, so the pressure must go up by 3. The way we set this up was we said 1 atmosphere gets changed by the ratio of the volumes. Since volume goes down, pressure must go up. So we put the big number on top, small number on the bottom, and that's how we get 3 atmospheres. So the answer is actually C. And the tricky thing here is to realize that the total volume of 3 liters still gave us 1 atmosphere. If we were to add all of these 3 atmospheres into 1 compartment, and that's exactly what we're doing here, then you would add the pressures. That'd be another way of thinking about it. If we have 1 atmosphere here, and these get cut in half with 1 atmosphere in each, and then we're putting this gas into here and this gas into here, you're essentially combining the pressures, and that's how we get 3 atmospheres. So there's more than one way of thinking about it. Here is another qualitative style question, even though we have some numbers. The figure above represents 3 sealed 1 liter vessels, each containing different inert gases at 298 Kelvin. The pressure of argon in the first vessel is 2 atmospheres. So here's argon, and we're at 2 atmospheres. The ratio of the numbers of argon, neon, and helium atoms in the vessel is 2 to 1 to 6. And what they're saying here is that since argon is 2, neon is 1, and helium is 6. In fact, you can see that. This is 1. You can see that just from the number of molecules. Since this is 2, this is half as much. So we have 4 molecules here. We have half as much, 2 molecules here. We have 3 times as much. If you count, you should have 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that actually corresponds. And now we're going to, all the gases are combined and then put into a 2-liter container. And they want to know what the total pressure there is. So there's a number of ways of doing this. Again, there's going to be a possible misconception hiding. So what I propose doing is putting this gas into the 2-liter container, and since we are doubling the volume, the pressure gets cut in half. So 2.0 gets cut in half, and we end up with 1.0 atmospheres. Because anytime you double the volume, you half the pressure, is the idea. And then when you put this 1 liter tank in here, again, we're doubling the volume because we're going from 1 liters to 2 liters, so you can say we half the pressure. So that neon gets us 0.5 atmospheres due to neon. And then the last thing, we have 6 atmospheres from helium, so we go down to 3 atmospheres from helium for a total. And then you can add these up for a total of 4.5 atm, 4.5 atmospheres, and that is the answer. So both of these questions are similar, and they relate to the adding gases or putting them together and so forth. And because the volume is changing, this is one way of looking at it. Okay, why don't we do more of a quantitative style question. So here we have a sample of a 0.01 mole of oxygen gas. It's confined at 37 degrees Celsius and 0.216 atmospheres. What would be the pressure of this sample at 15 degrees Celsius and the same volume? So now they're asking us to solve for the new pressure. So we can do this as T1, T2, P1, P2, as we've done in the notes. Our original temperature then is 37 degrees Celsius. Now remember, we have to use Kelvin. We cannot use Celsius because Celsius is not an absolute scale. It contains negative numbers, which will mess us up in calculations. So 37 degrees Celsius, add 273, and we should get ourselves 310 Kelvin. Similarly with the 15 degrees Celsius plus 273 gets us to 88? 288 Kelvin. So T1 is 310, T2 is 288, both these in Kelvin. Our original pressure is 0.216 atm, and we want to know what our final pressure is going to be. So using the ratio method, we've got 0.216 multiplied by the ratio of the temperatures. Now because temperature is decreasing, when temperature decreases, pressure decreases. This is the Gay-Lussac's law, which says temperature and pressure are directly related, up, up, or down, down, either way. So temperature going down will make the pressure go down, so we'll put 288 on top and then 310 on the bottom. And this will give us our new pressure. Now this is actually going to be a little tough to calculate, and remember, you cannot use calculators. So really the way to solve this one is to try to rule out any answers that don't seem plausible. So first of all, our pressure eventually goes down, we should end up with a smaller pressure because we have 0.216 atmosphere, so we should be below that. So 0.533 is out automatically, and so is 0.233, because both of these are actually higher pressures. And it comes down to these three that are left. Now, the decrease here is actually not very big. So this ratio is actually 288 over 310 is a little less than 1, probably around 0.9-ish or so. And so we won't have a huge decrease. For example, we will not get down to 0.0876 because that's roughly half. Actually, even less than half, more of a decrease than half. So that's out. And it's between 0.175 and 0.201. And here I would just do a guess. And the guess is that it's going to be 0.201 because according to this ratio doesn't look like it affects it by too much. It affects it by a little bit. So the 0.216 just goes down to 0.201. Another way you can think of it is roughly 288 out of 310. This is roughly a 10% decrease because from 310 to 288 you have somewhere in the 20s or so. It's actually 22. So it's actually less than 10% decrease. And so 216 down 10% would be down to 0.2, and we didn't quite go down by 0.2. So that's the way we can rationalize this. That would be the answer. Okay, let's do one like this. A 0.03 mole sample of ammonium nitrate is placed, solid ammonium nitrate, is placed in a 1 liter evacuated flask, which is then sealed and heated. The nitrate decomposes completely according to the balanced equation above. The total pressure in the flask measured at 400 Kelvin is closest to which of the following? So, and we're given the R constant. So this required the use of PV equals nRT. And essentially we're going to solve for pressure, which rearranging gives us nRT over V. Now in this case, what we've got is we have 0.03 moles of our starting reactant, and the reaction is balanced for you. And notice that you get 2 moles, actually 3 moles, 2 moles here and 1 more mole here of gas from 1 mole of reactant. So in essence our 0.03 moles becomes 0.09 moles of gas. That's just from the balanced equation, because we have again 3 moles to 1 mole of our reactant. So that's what we will put for N. So go ahead and put that for N. We get 0.09. R is a constant that's given to us as 0.082. Temperature is 400 Kelvin. And volume, nicely, is just 1 liter. So we're dividing all this by 1. So this will be, let's see if we can multiply the top numbers. It looks like it's a little difficult to do. But here, let me show you a trick that will help us do this. These two numbers, 0.082 multiplied by 400, can be represented like this. I'm going to move this decimal place over to the right twice, and I will move this decimal place over to the left twice, so they will compensate each other. Essentially, I'm making the first number 100 times bigger, second number 100 times smaller, so I'm evening out. So I end up with 8.2 multiplied by 4. So this is roughly 8 times 4, which is roughly 32, just being really rough. And then we then have to multiply by 0.09. So 0.09 you can say is roughly 0.09 is roughly at like 0.10. So really it's taking a tenth of 32, which gives us roughly about 3 atmospheres. So see if you can rethink how I did this. The trick was really this portion right here was the trick. So in fact the answer is 3 atmospheres. So a mathematical problem that looked like it was a little too difficult comes out not to be too bad. And again, you always have the multiple choice present, so you want to pick the number closest to the one that matches. Here's another similar example, except here we have a magnesium being added to some hydrochloric acid, at 0 degrees Celsius and 1 atmosphere of pressure, what volume of H2 gas can be obtained. So here we actually have a reaction, and we have to write out the equation. So we have magnesium with hydrochloric acid. This is a single replacement reaction, so you'd have to know your reactions in order to be able to do this, and we'll try to review these in class. So magnesium replaces hydrogen and gives you magnesium chloride and hydrogen gas. Quickly balancing the equation reveals that we need a 2 in front of the HCl, and this will actually be important. So now what we're asking is how much of the H2 gas will form from the reaction of 100 mils of 0.4 100 molar HCl. So we're given HCl. HCl is aqueous, so we're adding HCl through molarity. So let's find how many moles of HCl we have. Remember, moles is molarity times liters. So in our case, molarity is 0.400 and liters is 0.100 because we have 100 milliliters. So 0.100 times anything just makes it 10 times less. So our number of moles, N, is actually 0.04 for O. The rest of it is so this is 0.04 moles of HCl. So notice it's a 2-to-1 ratio of HCl to H2, which means we have half as much hydrogen. So this actually becomes 0.02 moles of hydrogen. So this is then what we're going to put into PVNRT. Now, you could do PVNRT, or there's actually a shorter way of doing it. And the shorter way uses the fact, and this is a good fact to remember, that 1 mole of any gas actually takes up 22.4 liters of that gas. Actually, if you plug 1 mole into PVNRT under standard conditions, you'll get out 22.4 liters. But this is a good factoid to have with you. Memorize. This will help you solve some of these problems a little faster. So really, since we have a fraction of a mole, all we have to do is multiply this fraction of a mole times 22.4 liters, because we know that 1 mole gives you this much, so a fraction of a mole, let's take the fraction out. So we can utilize our little method of swinging the decimal place over to the right twice, and then we'll swing it back to the left again. So if we swing it twice, we get 2 essentially times 22.4, which gets us 44.8. And then we'll swing it back to the left, which gets us 0.448 liters, which is actually 448 milliliters. So that's how I would do this problem. Now you could plug this into PVNRT. In fact, if you want, we can quickly do that. Our PVNRT, our pressure, our volume, we're being asked for the volume. Our volume will be nRT over P, and here is 0.02, so we get 0.02. R is 0.0821, and temperature is 0 degrees Celsius, which is 273, and we're getting a bit tight here. And luckily the pressure is 1. So we end up doing 0.02 times 0.08201 times 273. So these two numbers multiplied together, if you multiply these two numbers together, you could do the same trick we did previously, where you move the decimal place over twice this way and over twice this way, and you end up doing 8.2 times 2.7. So this roughly is 8 times 3 again. So 8 times 3 gives you roughly 24. And then 24 times 0.02, I know this is getting a little crowded, times 0.02, you can do the same thing here. Move it to the right twice, and you get yourself to 48. And then move it back to the left, and you get 0.48. So, and it's kind of close to this number, so you can pick among the numbers. That would be another way of doing it. But I would probably not do PVNRT, especially because they do not give you R, the constant R. You would use then this relationship, and they are relying on you knowing this relationship, that 1 mole of a gas is 22.4 liters. Okay, how about we finish up with a question that relates the speed of molecules to their temperature. So we talked about the distribution of speeds. Remember, anytime you're checking the temperature or the speed of a sample of molecules, say if you have a gas in a container, it turns out that the individual gas molecules have a certain speed, but since we have billions upon billions of them in any small amount of gas, we should really think about it as a population. And the way we do population studies is we use statistics. And we have this curve. This is called the Boltzmann distribution. And essentially what you're seeing is that most of the molecules have roughly an average energy. A few have a very high energy, a few have a very low energy, or speed. So when it says here, which of the following graphs shows the speed distribution of the same molecules at a lower temperature? So at a lower temperature, what you have is essentially you have the molecules slow down. So you have most of the molecules will have a lower speed, and the one that matches, this one, the dashed lines show it more molecules having a higher speed, so this one's out. This one also shows more molecules having a higher speed. This one's out. So it's between these two. Now this one's no good. B is no good because it reduces how many molecules we have. Number of molecules here. It makes this curve smaller. So we're not reducing how many molecules we have. We still have to have the same number of molecules. It's just they're going to slow down. So that's why this is actually the answer. D is the answer. Again, if you find a question like this that you have no idea about, no worries. You will see questions in the AP exam that you do not understand how to do, and just take your best shot. Okay, we'll actually do this then in the this concludes our lesson 5.